All right, students, welcome. Today, we are diving into a topic that is an absolute game changer for your exams, whether it's WAEC, JAMB, or NECO. We're talking about the electromagnetic field. It's kind of like the invisible engine of our modern world, and we're about to make it totally visible for you. Let's jump right in. So, let me just start with a question. Ever stop to think about what invisible force is powering literally everything around you? I mean, the phone you might be watching this on, the lights in your room, all of it. What is it? Well, for starters, this force is the secret source inside every single electric motor. You know, the thing spinning fans, blending your smoothies, even powering electric cars. And it's not just about using power, it's about making it. This is how we generate the electricity for our homes, our cities, all thanks to these massive generators and transformers. That's right, it's the electromagnetic field. And I promise you, by the end of this quick explainer, you're not just going to understand how it works. You're going to know exactly how to crush any exam questions that come your way. So, what is this thing really? Well, put simply, an electromagnetic field is just a region of space where a charged particle would feel a push or a pull, from electric and magnetic forces. And what does it come from? It's all about electrically charged things that are moving. In other words, electric currents. Okay, let's start with the absolute basics. How do we even make these magnetic fields? The key thing to remember is super simple. Moving charges, that is an electric current, that's what creates a magnetic field. Let's look at the two main shapes you absolutely have to know. Okay? Check this out. On the left, you've got a simple straight wire with current. It creates these nice circular magnetic field lines all around it. But look what happens when we take that same wire and coil it up into what's called a solenoid. Suddenly, the field inside becomes incredibly strong, super uniform. It basically acts just like a powerful bar magnet. That simple change in shape is a total game changer. So, how can you figure out which way the field is pointing? It's actually pretty easy. You use what's called the right hand grip. Seriously, hold up your right hand right now. Imagine grabbing the wire. If you point your thumb in the direction of the current, the direction your fingers curl, that's the direction of the magnetic field. It's simple, it's effective, and you will definitely see it on your exams. And we can even calculate just how strong that field is. Now, I know this formula might look a little scary, but trust me, it's not. B is just the field strength, and it really just depends on two things. N, which is how many turns of wire you have in a certain length, and I, how much current is flowing. It's a direct relationship. The more turns you pack in, or the more current you pump through, the stronger your magnet gets. Simple as that. Okay, so we know how to make a magnetic field. Now for the really cool part. How do we turn that invisible field into a real useful force? This right here is the fundamental idea behind every single electric motor in existence. And here's the magic formula for it. F equals BIL sine theta. F is the force we're looking for. It depends on the magnetic field strength, B, the current in the wire, I, and the length of the wire that's actually inside the field, L. The main takeaway is this. You put a current-carrying wire inside the magnetic field, and nature will push on it with a force, period. And just like before, there's a handy trick to find the direction of that push. This is Fleming's left-hand rule. And for motor problems, it is your absolute best friend. Go on, hold up your left hand, point your forefinger for the field, your middle finger for the current, and your thumb. Your thumb shows you the direction of the thrust or the force. Just remember FBI, field, current, thrust. Easy. Now, let's flip this whole thing on its head. We just used electricity and a magnet to create motion, right? So what if we used motion and a magnet to create electricity? This is called electromagnetic induction, and it's the idea that powers every electric generator lighting up our world. The genius Michael Faraday figured this out, and his first law is just beautiful. It basically says if you change the magnetic fields going through a coil of wire, what we call magnetic flux, you will create a voltage in that wire. You don't need a battery. all you need is a magnet and some motion. It's incredible. His second law puts that amazing idea into a formula. The voltage you get, E, depends on N, the number of loops in your coil, and how fast you change that magnetic flux. So, what's the bottom line? The faster you wave that magnet around or the quicker you change the field, the more voltage you're going to generate. But wait a minute, what's up with that little negative sign? That minus sign is so important. It comes from something called Lenz's law, which is really just a statement about energy. It says the new current you create will flow in a way that makes its own magnetic field to fight the change you're making. It's like physics saying, nope, you don't get free energy. You always have to work against the opposing force. All right, enough with the theory. Let's put this knowledge to the test and see exactly how these ideas show up in real exam questions. This is where you are going to start feeling really confident. Okay, here's a classic from a WAEC paper. It's a straight-up definition question asking about Lenz's law. Just take a second to look at the options. Which one has that feeling of opposition, that fight we were just talking about? If you picked D, you are spot on. The key word is oppose. Now, here's a super common trap. People mix up Faraday's laws, which tell you that you get a current and how big it is, with Lenz's law, which only tells you which direction it flows. Lenz's law is all about that opposition. Okay, ready for a JAMB question? This one's a bit of a thinker. It asks which of these particles gets knocked off course the most by a magnetic field. Remember, that magnetic force needs a charge to act on. So where do we even begin? Let's break it down like a detective. Step 1. Get rid of anything that has no charge. So gamma rays and neutrons, they are out. They won't feel a thing. Step 2. Now we compare our charged particles, beta rays and alpha particles. The key here is the charge to mass ratio. Think of it like this. It's easier to push a small light car than a giant truck, right? Even though the alpha particle has more charge, it's also thousands of times heavier. That tiny lightweight beta particle gets thrown around way more easily by the force. So the conclusion is clear. Beta rays are deflected the most. Fantastic work. We've covered a ton of ground. So let's just do a quick final review and pack your essential toolkit. Everything you need to walk into that exam hall feeling ready. Here they are, your absolute essentials. Take a second to burn these into your brain. You've got the solenoid formula for finding field strength, the motor force for figuring out the push on a wire, Faraday's law of induction for calculating voltage in a generator, and the transformer equation, which uses that same principle to change voltages. If you can master these 4, trust me, you are going to be in excellent shape. So remember this, you're not just learning physics to pass a test. You're learning the fundamental rules that run our entire electrical world. From the tiniest motor to the biggest power grid, you now understand the invisible force that makes it all tick. So, the only question left is, how are you going to use that knowledge? Thanks for tuning in. Great job following along. If you found this tutorial helpful, don't forget to subscribe to our YouTube channel for more easy-to-understand lessons. And hey, want to practice more questions and get step-by-step solutions? Visit ExamKP.com right now and keep learning smarter.